Hi everyone, my name is Zoe Yan. I'm in Princeton University. I'm currently a postdoc in the group of Wasim Bakr. And before I begin, I'd like to thank the organizers for the invitation at this wonderful workshop. And today I hope to squeeze in two exciting topics where we have some relatively new experimental results. The first one will be on studying lattice spin models with quantum gas microscope with the system of dipolar molecules. And secondly, I'll tell you about a little bit of our latest work regarding kinetic magnetism in a Fermi-Hubbard simulator. Maybe I'll begin with a broad overview of why we think quantum simulation of condensed matter systems with ultracold polar molecules is a very exciting topic. So there are many experts in the audience, but for those of you who are not, here's a little bit of background and why polar molecules are now a very nice frontier area in the AMO sciences. So for the non-experts, here's a simplified level diagram of a diatomic molecule. Like the hydrogen atom we all know and love and study, it has, electronic states, hyperfine states, but unlike a simple atom, it also has quantized vibrational and rotational levels. And that rich internal structure gives us a lot of tunable degrees of freedom in the lab. And primarily, that structure is what gives rise to a very useful quality, which is a long-range anisotropic dipole-dipole interaction, an electric dipole interaction. And this gives us a handle to realize a lot more flavors of different many-body Hamiltonians. Molecules also have other advantages, a wide range of energy levels with convenient control knobs, as well as demonstrated long hyperfine and rotational coherence times. In the past decade and a half, I would say that there have been two complementary approaches towards forming these ultracold polar molecules. The earliest and by far and away most promising in terms of realizing very large ensembles with very high phase space densities was pioneered by the Jilla group of Debbie Jin and Jun Yi, and also Kongquen in the audience. And this is basically association of molecules from already ultra-cold atoms. Cold atoms, we already know many techniques to laser cool, evaporatively cool, so we basically stick them together and we can perform optical manipulations to control them into the absolute ground state. And this has resulted in brilliant work across the world, even creating degenerate Fermi gases of polar molecules rather recently. And more recently, there has been a strong thrust toward developing direct laser cooling of molecules. This is hard because they don't really have convenient optical cycling transitions. Nevertheless, there have been the formation of magneto-optical traps and recently control at the level of putting in calcium fluoride molecules, for instance, in single optical tweezers. Now, this is very exciting because you have fast cycle times, single molecule detection and control capabilities, but right now, as of yet, these types of laser-cooled molecules are not motionally very cold, so they are probing spin physics and not yet itinerant degrees of freedom. We at Princeton, in Wasim's group, would like to combine the single molecule detection and control, but with the first method of forming large ensembles of molecules. And we would like to use that in conjunction with a technique called microscopy, basically marrying the ability to have these tunable degrees of freedom from cold polar molecules with the ability to trap them in optical lattices with very short lattice constants and perform microscopy so we can resolve single site occupancies of each individual molecule. And for atoms, microscopy is by now a well-established technique involving many groups around the world, and we want to bring this technology to the world of polar molecules as well. And to start with, here's how we create these molecules in the ground state. We definitely need to recognize that the molecule we use, which is sodium rubidium, was first controlled and tamed by the group of Dajun Wang at the Chinese University of Hong Kong. And we basically follow the same recipe with some minor modifications. We prepare ultra-cold rubidium and sodium mixtures into dual Bose-Einstein condensates and then load them into a two-dimensional optical lattice, a square lattice. We use a Feshbach resonance to associate these into weakly bound dimers, but we don't want to work necessarily with Feshbach molecules. We want to use a strong interaction that's afforded to us with ground state molecules. So we perform a two-photon coherent optical transfer of the Feshbach state into the absolute ground state. And our first result was just at the Feshbach stage, demonstrating that we could do microscopy. These molecules do not have convenient optical cycling transitions, so what we do is we actually break them apart with a radio frequency pulse. We throw away one of the species and laser cool and fluoresce the remaining rubidium atoms and collect it on a high numerical aperture microscope objective. And if you recover enough fluorescence counts, you can create single snapshot images like so, where each fluorescence is a marker or a tag of where an initial Feshbach molecule had lived in the lattice. And this is its digital reconstruction. And you can see that our average filling is still low compared to the state-of-the-art in atomic quantum gases, is around 15 to 20% in the center of the gas. But the important thing now is with the microscope, we can detect individual site-resolved quantum correlations. But here I'm talking to you about long-range interactions. So how do we turn that on? And more importantly, what do we do with it? So we are very inspired by a lot of older proposals, including the one listed here, to study systems of quantum relevant to quantum magnetism with these polar molecules. These molecules are frozen on the lattice site, so right now they do not have an itinerant degree of freedom. However, because they are long-range 1/r³ interacting, we can hope that even at our 15 or 20 or even like 10 or 7% occupancy, there will be some correlated many-body state that arises due to this long-range interaction. And how does this dipole moment get formed? Well, we create all of our polar molecules in the ground electronic, vibrational, and rotational state n equals 0. So in the absence of any symmetry-breaking external field, there is no dipolar interaction, right? So that's not exciting. One way to get a dipole moment in the lab frame is to couple two opposite parity rotational states with a gigahertz microwave drive. And by either dressing or in what we do, creating a superposition of 0 and 1, or as I'll refer to from now on, up and down, we will create this lab frame rotating dipole moment that has non-zero dipole-dipole interactions with all of its neighbors. So if you're from Rydberg land and you're familiar with creating dipolar interactions with Rydberg S and P states, this is pretty much the same picture that you should have in mind. So let's go and realize some interesting lattice spin models. So these are condensed matter textbook models thought to capture a lot of neat emergent phenomena when it comes to magnetism. So a very general way you can write this lattice spin Hamiltonian is an XYZ model, where you have the Pauli XX operators coupling YY and ZZ, which is the Ising term, and they can come in at various strengths. However, the natural Hamiltonian that we implement with the scheme I just showed you a slide ago is a spin exchange Hamiltonian without the Ising term. XX and ZZ are equal in strength. And this dipolar interaction is what gives us this exchange constant. This falls off as 1/r³, and the nearest neighbor interaction for our molecule and lattice constant is approximately a kilohertz. So a kilohertz is a pretty high energy scale in these cold atom experiments and is the dominant energy scale for the experiment I'm about to show you. Of course, we were heavily inspired by this landmark experiment by the Gilla group 10 years ago at this point, where they had polar KRB molecules in a three-dimensional optical lattice. They performed a Ramsey experiment using two rotational states, and as you might expect, saw dephasing over time. But what's really neat about this experiment is that their Ramsey contrast, dephased non-monotonically. And these wiggles were exactly due to the nearest neighbor dipole-dipole interaction. And I will also mention that the spin exchange Hamiltonian has by now been studied with a multitude of other systems. And the field is rich and very exciting. But at Princeton, we can leverage our microscope to measure slightly different quantities now. So we study correlation dynamics in this XY spin exchange Hamiltonian. And like the Gilla experiment, we first prepare everything in the rotational ground state, spin up. We quench at time 0 to the plus x state, wait for Ramsey precession, have a spin echo in the middle, and perform the readout pulse at the end. Now, we choose the phase of this readout pulse such that in the absence of any dephasing dipolar interactions, we would expect all of our molecules to end in the spin down state after a whole pi pulse, essentially. So if we look at our fraction in up versus time, you can think of this as magnetization. If there were no interactions at all, this should probably just be 0 for all time. But what actually happens? Well, these black fluorescence images are single snapshot microscope images showing that at early time, small pairs, clusters of molecules start to pop up. Intermediate times, these clusters get larger, and at late times, pretty much the entire ensemble has dephased. And what we can do with the power of microscopy is measure individual correlator functions, such as this up-up correlator. How likely is that a molecule to appear next to another molecule as a function of their separation? And this is what's shown in the bottom left. At early times, the nearest neighbor molecules become very correlated in their appearance. It's because the nearest neighbor interaction is the dominant interaction because of this 1 over r cubed fall off of the dipole interaction. At intermediate times, you can see that the diagonal neighbors have become entangled until at late times, the entire ensemble is dephased and many-body entangled. We can plot individual correlators versus time in a clearer picture, and from this, we can more easily understand the wiggles in the magnetization. So the dominant wiggle comes from the nearest neighbor interaction, which is oscillating at the fastest time scale. The diagonal neighbor is 1 over r cubed weaker, and et cetera for the one further neighbor. So not only can we study dynamics in this XY spin exchange Hamiltonian with spatial isotropy, we can also manipulate our quantization axis to make V of r anisotropic. So if I show these s and p orbitals here, maybe a hand-waving picture is initially we polarized or we quantized our molecules perpendicular to the plane of the lattice. So all of these donut and sphere superpositions, you can just see by inspection that everything is isotropic versus radial position. But if we quantize in parallel to one axis of our optical lattice, you can see that these donuts become tilted, and there should be repulsive interaction along one axis and attractive along another. And that is exactly what we find when we perform that experiment. The top is the theoretical interaction potential, just this 1 minus 3 cos squared theta term that we all know and love. You can see it's repulsive and attractive along different directions, and the magnitude is also different. And in our correlations, we find that the y nearest neighbor oscillates twice as slowly as the x nearest neighbor in accordance with theory. And I will just flash these results, but we can not only tune our spatial isotropy, but we can also control our spin isotropy. So not only can we be restricted to these XY spin exchange Hamiltonians, but with the power of Floquet engineering, by applying a rapid burst of different microwave pulses with phase control, we can engineer something analogous to an XXZ spin Hamiltonian. So the outlook for this section, I will just say that molecules are very promising for study all sorts of spin models because of their long rotational and nuclear spin coherence times, their tunable interactions, where we have demonstrated that you can pick whatever you like in terms of XYZ Hamiltonians. And the microscope is quite nice for quantifying these correlations between individual molecules. And what we're working on next at Princeton is we definitely want to increase our phase space density. One way to do that might be to evaporatively cool molecules with this technique called collisional shielding, and hopefully one day to achieve Bose-Einstein condensation in a gas of polar molecules. So maybe I'll abruptly switch topics, and even though this is a long-range interaction workshop, I hope you'll forgive me if I go back to an experiment, a separate experiment that has only short-range atomic interactions. But we do have some recent rather neat results on this experiment as well. So for a little bit of background, let me talk about why we are interested in studying this Fermi-Hubbard Hamiltonian. So the Fermi-Hubbard model is a very nice, simple model, easy to write down with two terms. It describes initially, or originally, electrons of spin up and down moving on lattice in a single band in the tight binding regime. And the electrons can tunnel from site to site with some tunneling constant, and two electrons of opposite spin can occupy the same site and pay the price of some on-site Hubbard interaction U. So initially, this motivation was to be a basic model for the high TC cuprate superconductors for the Fermi-Hubbard Hamiltonian on a square lattice. And the cuprates are these very interesting materials that could be of technological importance if we ever manage to engineer them to have room temperature superconductivity. And the phase diagram is thought to be the following. You have temperature versus, here it's electron doping. At half filling, the state forms a Mott insulator with anti-ferromagnetic correlations, and as you dope more, you enter the pseudo-gap phase and this exotic D-wave superconducting phase with maybe a quantum critical point in the middle. Who knows? But so what has the cold atom community contributed to the study of Fermi-Hubbard physics? That would be too much to list on one slide, so forgive me if most of the results in the community are not shown here. I'll just briefly flash what various quantum gas microscope groups have done recently around the world. In 2016, there were amazing results where within the Fermi-Hubbard regime, two-component fermionic atomic species were found to form Mott insulators, so n equals 1 filling for repulsive interactions. And moreover, upon cooling that a little bit further, people were able to see anti-ferromagnetic correlations within those Mott insulators, so a quantum Néel checkerboard. And people have also doped away from half filling and seen a variety of phenomena, including strange metallic behavior, magnetic polarons of charge impurities doped by a cloud of spin imperfections, as well as geometric strings. But I will say that this plain vanilla Square Hubbard model has been studied extensively by the community, but the community maybe could also look beyond this plain vanilla square geometry. Novel geometries could add something new, some new flavors, including spin and kinetic frustration, novel dispersion relationships, and interesting topological phases of matter even. So let's look at maybe another very simple lattice geometry, which is the triangle, right? And let's compare and contrast the square and the triangle. So in the square, let me go back to what many of you are no doubt already experts in. Why is anti-ferromagnetism favored? So there's this phenomena called superexchange where that directly leads to favoring of AFM order. So if you have two electrons of opposite spin in adjacent wells, they can undergo a second-order tunneling process where momentarily they occupy the same site and then tunnel back. And because the sign for fermions of the superexchange is negative, this depresses the overall energy. And so that's a hand-waving argument for saying why the checkerboard, the quantum checkerboard, is favored as the ground state at 0 temperature. But this nice, neat argument breaks down on a triangular lattice. I mean, superexchange definitely still exists, right? That's not different. However, there's this spin frustration where the nice story is it breaks down. If you put a spin up next to a spin down, then the third site becomes confused. And because of this confusion, theory has now, by now established that at least in certain regimes of U over T, the ground state is this 120-degree spiral phase. And recently, there have been two really amazing results on both microscope groups realizing Mott insulators within isotropic triangular Hubbard geometries, and they have witnessed spin correlations consistent with this spiral antiferromagnetic order. So I need to highlight the first of these two results, which is Peter Schaus's group in the University of Virginia. Here they have plotted the spin-up correlation function that they measure across, for instance, the 6 nearest neighbor bonds. They're all antiferromagnetic, and this is consistent for a given temperature with this spiral 120-degree order. Marcus Weiner's group at Harvard has recently put out a beautiful paper where not only do they see this negative SZ-SE correlation at half filling, but they're able to both dope with holes and dope with charges and see that there is a distinct asymmetry between particle and hole. And this is very different, very cool, because if you remember on the square, there's particle-hole symmetry. That would be completely reflection symmetric, but the triangle lattice is not bipartite, so you wouldn't expect any particle-hole symmetry, and indeed that's what they find. And there's this very intriguing bump where they see ferromagnetic correlations, which I will come back to later. So a theorist might ask, well, if the triangle is as interesting as you say, like why has it taken so long for people to realize this? Like the triangle is, its flat head is one less than the square, isn't it easier? But I will say that for every implementation I know, the triangular lattice does involve more beams hitting the atoms. And from an experimentalist perspective, the number of beams, the difficulty does not go linear with the number of beams. It's like an algebraic scaling or worse. So maybe that's why the community took that amount of time to implement triangles. But here we are. However, there is a nice shortcut. And this credit goes to the MPQ group, the rubidium microscope group of Emmanuel Bloch and Johannes Zeyer recently put out a paper in January of this year where they have a programmable interferometric lattice, and it's beautiful and very elegant. I will spend one slide to tell you about technical details because I think this is super amazing. So imagine that you have this blue lattice only. You have a laser going 1 pass, 2 pass, reflective back from retroreflecting mirror, 3 pass, 4 pass. That will create a square geometry. You can probably picture that. And indeed, this bow tie lattice is what many groups have used, including at Princeton, to create square lattices in our previous work. But let's say you add an orange superlattice. This superlattice is of the same, almost the same wavelength as the blue, but it's slightly detuned, so the orange and the blue do not interfere together. But the orange is back reflected on the same mirror and forms a one-dimensional lattice on its own. Now, imagine when you start with the blue and slowly crank up the orange power, you'll start to create a 1D lattice along the diagonal, or this diagonal. But that creates tunneling along 2 diagonal neighbors. So initially, you had the base lattice, which is the solid black line, that's square, but then you can tune up and up T prime, this diagonal tunneling, and it's quite easy to see when T and T prime are equal. This is a completely isotropic Fermi-Hubbard simulator that you've created. So Emmanuel recently visited Princeton, and he mentioned that the grad student was the one who came up with this idea, which is just amazing. Wasim saw this paper, and within the month, grad students at Princeton had basically built this and were taking data with it. So another important detail about the Princeton microscope is that we are able to look at the full information. Our microscope is both spin and charge resolved. So I won't go into the technical details of how, but basically for every snapshot we take, we are able to separate the ups and the downs and take a simultaneous fluorescence image of both with high fidelity. So that gives us double the information of what usual microscopes do, and is quite nice to construct various correlation functions. So at Princeton, we were also able to recover these 2-point spin-spin correlators, like the ones I showed you from the Virginia and Harvard group. So on the left, you see raw images of our 2 spin states, and on the right, this is our spin-spin correlator, just the 2-point for now. The center site is meaningless, but the 6 blue sites are the nearest neighbor bonds. You see they're strongly anti-ferromagnetic, and then the next nearest neighbor is weakly positive, so on and so forth. So here I'll take a brief detour to tell you about something that we hope is qualitatively new that we're seeing in contrast to past work. And that is this phenomena of kinetic antiferromagnetism. So there's this beautiful paper from 2005. Let me just read you some highlights. The motion of a single hole in the infinite U Hubbard model with frustrated hopping leads to weak antiferromagnetism of kinetic origin. So let me break down this paper for you. Basically, they go to infinite U. So J, superexchange, which is basically T squared over U, it dies out. There should be no more superexchange. But even so, they show that if you put a single hole, that whole motion mediates an effective exchange coupling between the spins in the near Mott insulator. So that means that you have created a new type of kinetic antiferromagnetism. And this may remind you of this very famous Nagaoka theorem from several decades ago. So this Nagaoka theorem, or at least one version of it, is that on bipartite lattice geometries, for example, you have this very strange type of ferromagnetism arrive. So you go to the infinite U limit, you go to half filling but dope with one hole, and interference from the hopping on, for instance, the square plaquette will cause the ground state to be ferromagnetic. And this is kind of in contradiction what we might naively expect from something like the Lieb-Mattis theorem. So the picture here is if you go to half filling plus one hole, you have 3 particles. You have 2 potential ground states, the total spin S equals 3/2, or the total spin S equal 1/2. Nagaoka proved that S equals 3/2 will be favored as the ground state. And there's a hand-waving argument, which is that the constructive interference of the whole motion and the spin polarized background actually lowers your kinetic energy and favors ferromagnetism. So what is the story on a non-bipartite lattice that has destructive interference? So the original variant of the Nagaoka theorem no longer applies, but there's something that is very related that pops up. So let's consider the triangular lattice, either in a hole in a spin polarized background or a hole in the vicinity of a spin flip. Even on a single plaquette with no interactions, with infinite interactions, you can just do an exact diagonalization and find that this rightmost column is favored. So a hole really likes to bind to an antiferromagnetic bond, and this is, many people call this a magnetic polaron or a spin polaron, and by now there's a lot of theory work that has been put forth to explain how exactly this mechanism leads to lower kinetic energy, and the polaron binding is on order T, the tunneling, rather than J, the superexchange. And so we tried to take snapshots of this spin polaron. And to do that, we need to look at correlators across a plaquette, or 3 or more sites. And so these are our 3-point correlators. So we're looking for a hole. This is with hole doping and weakly repulsive U over T. And then we look at what the spin-spin correlators are in the vicinity of that hole. And we subtract off the trivial background. And immediately you can see that all 6 nearest neighbors are negative to outside of our error bars, whereas the further background becomes ferromagnetic. What about the other type of impurity? What if we dope with charge? Therefore, we will have many double occupancies, which also can form a spin impurity. And in the case of the double occupancy, the sign flips, and the sign of the magnetic ordering becomes ferromagnetic in the nearest neighbor vicinity. So the picture you should leave with is that holes will cluster with antiferromagnetic bonds, and doublons will cluster with ferromagnetic bonds. And so we can see that this is quite robust to various types of doping, various degrees of doping. So here we see this conditional SC-SC correlator versus doping, with one being half filling. And the pink data points are our hole correlators, which are negative, and the green data points are our doublon correlators, which are positive. So we believe that this hints at the Nagaoka mechanism seen for the first time here in an extended cold atom sample. And I would like to point out that there have been 2 recent examples of kinetic ferromagnetism witnessed, one in Moray transition metal dichalcogenide materials that form a Fermi-Hubbard simulator with triangular geometry, as well as the results that I mentioned briefly from the group of Marcus Greiner. So this kinetic magnetism is qualitatively different than superexchange, right? So we kind of want to distinguish where our magnetism arises from. And one way to distinguish kinetic versus superexchange magnetism is actually to go one further, looking at a 4-point correlator. And the reason we do this is that an SZ-SZ bond on a triangular lattice, by symmetry, it's part of 2 plaquettes, right? The left plaquette and the right plaquette. So if we were to restrict ourselves to saying only superexchange is allowed, we neglect holes, we neglect doublons, we look for SZ-SZ correlators conditioned on proximity to 2 single occupancies on the left and right. And we see that, yes, indeed, this correlator is negative for a range of dopings, so there is superexchange still, as expected. However, when we condition on one of these sites being a hole, not only is superexchange allowed, but this kinetic frustration is also allowed. And that, we see unambiguously, leads to a stronger type of antiferromagnetism. So this, for us, was a strong indicator that what we see is qualitatively different than superexchange. So I'm out of time. Brief outlook is that we would maybe even like to measure higher order bound states that are predicted, maybe even whole-hole pairing in certain regimes. And it's nice to see the spin polaron, but even nicer would be to measure its binding energy, maybe through going to different spin imbalances. And circling back to longer range interactions, we have a ways to go, but with the polar molecule experiment, we could potentially access extended Bose-Hubbard models, and on frustrated geometries, that should lead to a plethora of very exciting phases, including perhaps checkerboard supersolids. With that, I would like to acknowledge the team. This work was led by Wasim Bakr, and the Fermi-Hubbard work was carried out by students Ben and Max. Molecule team, grad students Lysander, Jason, Ravin, postdoc Yusuf, theory support from David, Alan, Eugene, and Ivan. Thanks for your attention.
So thanks very much for this wonderful talk. Questions? So maybe I can start with a question on the, regarding the last part. You showed some examples in in condensed matter systems with these Murray lattices. What other motivation is there to study? Is there condensed matter motivation to study the Fermi-Hubbard model on triangular lattices? I mean, the original motivation for Fermi-Hubbard being high TC superconductivity, is there anything in this line that?
Right, I would say it's not motivated so much by the Coop rates anymore, as you pointed out, but ferromagnetism is shockingly rare, and people still don't understand why, even though the Nagaoka theorem is a theorem and it holds in the limit of one hole, but people have shown that ferromagnetism doesn't survive in real samples because there's usually more than one hole, and that instability and why things change from ferromagnetism to anti-ferromagnetism is still not very well understood. So studying frustrated geometries might lead to insight on itinerant ferromagnetism, which again is pretty rare in materials and still not quite well understood.
Cool, thanks, yeah. Yes.
Very nice, very nice work. I have one question. So you said that you wanted to push the itinerant behavior of molecules. So in principle, even if there are losses, you could see xenosuppression. I mean, instead of needing necessarily the shielding, if the loss is very large, in principle, it can be further suppressed by xeno. Are you planning to, or have you seen any evidence of some dynamics when you make the lattice shallower, or?
Right. So we would love to see the xeno effect, and we believe we've seen hints of it, but so far we are really focused on just increasing our lattice occupancy because right now we can evaporate with 15% filling in our lattice of only like 100 molecules. So. But yeah, that would be definitely interesting to revisit. And you mentioned possibilities of itinerant behavior even without shielding. I'm still interested to see whether some of these hardcore models can be well applied, even in the absence of shielding, like if the on-site repulsion is strong enough. Thank you.
Time for maybe one more question. Okay, so, sorry, I didn't.
For the Fermi-Hubbard simulator, I guess, is there interest in spin liquid searches for different types of frustrated lattices?
Yeah, that's a great question. So initially, we were thinking, so I should preface by saying there are many theory proposals that in between U equals 0, which is a non-interacting system, and a very high U over T, which becomes a Heisenberg, this 120-degree spin ordering. In an intermediate regime, there is a non-metallic insulating phase, which some people believe to have a spin liquid phase, a quantum spin liquid phase. And there are correlators that are very difficult, but in principle possible. For instance, a chiral correlator, I think it's S1.S2 cross S3 or something like that, that could in principle lead to an indication of a quantum spin liquid phase. However, the temperatures that we would need to reach, I think right now would preclude us from seeing that in our system.
Right, so let's thank Zoe.